Hello everyone, welcome. This is class ECE317 Digital Signal Processing. Last time we have introduced something about the system and the Fourier transform. We can try to find the output use the help of Fourier transform, discrete time Fourier transform. And today we keep working on this topic. This is a ECE317. Oh, I need to turn this one. Am I good? Okay. ECE317. This is a which class? Monday, Wednesday class. Wednesday class for the 4th week. We can find the output of system. Actually, we have several ways, right? So for a system, for a LTI system, we have input, then we have output. So far, we have several ways to find this output. The first way, of course, this is a basic one. X of n, we plugging this in the equation. Then we can solve to find y of n. This equation is usually we can write in this way: summation of some coefficient, let's say a k, times y of n minus k, equal to summation some bk, some coefficient bk, times x of n minus k. And for the output y, how many terms do we have? Suppose k will run from 0 to some l, and here's k for the input side. K run from 0 to some n, right? So this is the first way. But usually this way is not easy to solve it. And the second way, we use a impulse response. We use impulse response. If we know what is impulse response, then the output is input convolution with impulse response. Right here, h of n is the impulse response. Impulse response. But of course, you need to know what is impulse response firstly. So you can use the first method, find the impulse response, but you do not need to use the first way for all the other input. Right? You use this way in the impulse. If input is impulse, you solve it, you get h of n, impulse response. Then for any other input, you just perform the convolution. Right? You don't need to solve that. Okay. But the convolution, it is also not so easy. Remember, you do the convolution, you can use the definition. That will be summation of x of k times h of n minus k for all the k's. Of course, you can also reverse the order. You put h in front, h of k times x of n minus k. You will have same result. You can use this way to calculate, right, the convolution, or list the table, right? You have h, you have x, then you times them together, then do summation in this way. You can have the convolution, right? So either way you can use. This way can give you a formula. And this way, in somehow it will be easy, easy to be handled. You just list the numbers, do summations. Yeah, seems not so hard. But this way, sometimes you get a result. It is not in formula form. Right? If you want a formula, this one might be better. Okay. Then third way, this is what we studied last time. We use Fourier transform. So basically, it's still this one. But we do this, go to the frequency domain. So things like that. We have x of n we perform the Fourier transform, which is now in the discrete time case, right? Discrete time Fourier transform. We perform this. We have capital X e to the j omega. Then I have h of e to the j omega. Suppose the system, we know this. Here the times. We do a multiplication. Right? We do a multiplication. Then we have y of e to the j omega. The result of this, the multiplication of these two, it is just this one. It is a result of this multiplication. And then we perform the inverse dtft. dtft with the inverse. Then we have y of n. So we want to calculate this output. We can use this way. We go this way, then we go this way, go this way, go this way, and going up. Then we have it. The system is still this system, right? The same way this, same system. Here, H, capital H, is a dtft. I write in this way: dtft of h of n. Right? Yeah, dtft. You perform Fourier transform. You have Fourier transform on this h. Then you can have this capital H. This is, we call this a frequency. This one. Right. So this is the third method. In this method, you need to perform dtft for the input and the impulse response. Then times them together. Then do the inverse dtft. All right. Okay. Now, okay, we base on, yeah, we can have three methods. Now we consider special case. If input is a sinusoid, what will happen? Okay. Now consider input x of n, which is e to the j omega 0 n. This one, this e to the j something, it means cosine of that one, right? Here, j times angle. This one, the part after the j, you think is angle. This is angle of this cosine, and plus j times sine of that angle. Okay. This is a Euler formula. Euler formula. Euler formula. Euler formula. So this kind of signal, it is a combine of cosine and the sine. Cosine in the real part, sine in the imaginary part. So this is a sinusoid. It's a combine of cosine and sine. It's sinusoid. It's still a sinusoid. Sinusoid. The frequency is omega 0. Because the frequency is omega 0. Then what will be the output? What will be the output? We can use any one as a method, so we can use second one. The convolution way will be easy one. You can also use the Fourier transform, but if you check the Fourier transform table, you will find in the frequency domain, this one will turn to be a infinite summation of infinite terms. Yeah, you can check the table by yourself. Here I don't do that, but I just tell you. This e to the j omega 0 n, if we go to the frequency domain or perform Fourier transform on it, the result will be a summation of infinite terms. Yeah, that's a lot. So we prefer do not use the Fourier transform. We just use the convolution to calculate. Alright. Then output. Then the output is y of n, which is input convolution with impulse response. Now we do the calculation just based on the definition. Is summation of xk xk, I use hk, alright, hk in the front, e to the x, here's x of k is this one, n minus k, right? So j omega 0 n minus k, and k run from negative to positive infinite. Alright, this summation is running for k, right? For all the case, but n is just n, right? Summation is not for n, so we can move n outside. This is a summation k run from negative to positive infinite, h of k times e to the j omega 0 n times e to the j omega 0 negative k, right? And I move this n term in the front, so it is e to the j omega 0 n times summation h of k e to the negative j omega 0 k, and k run from negative to positive infinite. Now we have this one. Alright, what is this? Any sense? Yeah, this is a Fourier transform of h. It is just this one, the frequency response. And of course here's omega 0, not all the omega, so this is omega 0, just for one omega 0. This omega 0 is a fixed number. Yeah. So it is a value of the frequency response when frequency is omega 0. And what is this part? You see, what is this part? Oh, it's the input, right? So this is just the input, x of n. So you see, what is the output? The output, now the output is this value times input. This is a very nice result. But of course, this is only for this kind of input. If input is a combine of cosine and sine with a fixed coefficient omega 0, then the output is also this one, but with different amplitude, right? You change your amplitude, you times h in front of it. Yeah. So the things like that. Here's h of n. You can also put this h of e to the j omega here. Then the input is x of n, now is e to the j omega 0 n. Then the output side will be y of n, which is, this is amplitude times it, right? So I put amplitude in front. The amplitude times xn, e to the j omega 0 n. Alright. This is a very nice property. The input side and output side will have same frequency if input side is a sinusoid, is a wave, right? It's a frequency wave. The output side is still same wave with same frequency, They have some change on in the front, in the amplitude. Not just amplitude, this also contains something with phase. So you change the phase and amplitude, right? The system changes the phase and amplitude, but keep the same frequency. This is a very useful feature for the linear system, LTI system. For example, I'm talking here, right? I have a microphone. I talk here. My voice go to the microphone, go to the computer, and the computer recorded. You think this is the whole system, right? And finally, in your computer, when you connect to my video here, you can hear my voice. That's my voice, not someone else. It's my voice. Why? Why is my voice? Because this is the voice you heard will be same. Will have same frequency with mine. Different people, the voice different because every people has different frequency. My voice have should be a frequency of mine, and my voice goes through the system out as an input, finally as an output in your side, but that output will have the same frequency with me. So you know, okay, this is the voice of Dr. Ninja, not someone else, right? Yeah. This is okay. All the things, the cell phone, the microphone, the radio. We all have this. We all have this feature. Keep the voice. Keep the frequency. All right. So this is why we use LTI in a lot of places. One of the reason. And you keep the frequency of voice. Keep the frequency of any kind of signal. Yeah, keep the frequency. All right. Okay, so this is just for the e to the j omega 0 n. Now, if we input this cosine, what will happen? If we input this sine, what will happen? Okay, now we look at here. So if cosine as input, cosine omega 0 n as input, we go to this h e to the j omega 0. What will be output? You can say this is what? This is the real part of e to the j omega 0 n. Right? And this system, this is a real system. And we suppose this is real system. We only consider real system. That means the equation, right? The system can be described by an equation. The equation, all the part of in this equation are real numbers. In other words, this equation is coming out from some model in the real world, some mechanical world, some digital, some mechanical system, some digital system, some circuit or something. Yeah, they coming out from the system in the real world. So all these AK, BK, they are real numbers. We only consider real numbers. And even you consider input X, Y. Now X or Y may be complex, but the system itself is real. All the coefficients are real. So this side must be a real one. You consider things like this. You use this imaginary thing. This is a complex thing, right? The complex thing contains both imaginary part and the real part as input. Then output side there will be e to the j omega 0 n times capital H of e to the j omega 0, right? The output, if this is input, output will be this one. This one contains both real part and imaginary part. Then the real part is this one. And what is this real part? Okay, we need to do some calculation here. E to the j omega 0 n times h of e to the j omega 0. I can write it as, okay, I put h in the front, as the magnitude of e to the j omega 0 times e to the j angle of this h of e j omega 0, then times e to the j omega 0 n. And this, I keep this magnitude, and these two I times them together. It is e to the omega 0 n plus angle of the h. Make sense? Are you familiar with this part for the complex numbers? Okay, now you just remember, you can write h in terms like this. Then from here to here, you times together, then you add the power together. So you add these two together, you get this. And then this is magnitude of h times this exponential power, so it is a cosine of exponential power j something, right? So j omega 0 n plus the angle, and plus j times the sine of omega 0 n plus the angle. Alright, so we have this. Then what is the real part? You see, this cosine is the real part, right? So the real part is magnitude of e to the j omega 0 times cosine of omega 0 n plus the angle of h e to the j omega 0. Now we have this one. So if cosine is the input, then output is also cosine with same frequency omega 0. But you have different phase and different amplitude. Both phase and amplitude coming from the frequency response. The magnitude of the frequency response, the phase of the frequency response. Oh, here, I'm sorry. This one here, omega is any value. You read this. Not zero, not circle here. No zero here. This is just omega. So any omega. But here's a special omega 0. All the omega 0s here in output, they are coming basically coming from the input. Input is this frequency, then output is this one. All the frequency is coming from the input. It's constant. Omega 0 is constant. And inside the block of the system, here's omega is just omega. So omega is variable. We know this variable basically from one period, right? It's from 0 to 2 pi, or negative pi to positive pi. But actually, you can use any period. So you can think omega is running from negative to positive infinity, and any one period from 0 to 2 pi is like a May part, is a May cycle, right? Okay, this is cosine. And the similar thing, we can have sine. Sine omega 0 n. This one as input, we go to the same system, h e to the j omega as a frequency response. Then output will be magnitude of h at frequency omega 0 times cosine of omega 0 sine. This is sine now. Sine of omega 0 n plus angle of h e to the j omega 0. Alright, so we have this one. And these, actually the similar thing, use this method. But this time is imaginary. I put im is imaginary. Imaginary of e to the j omega 0 n. Right? Okay. So if input is sine, we have this one. Alright. Then, okay. Now let's go more about this part. So what is this one? Right, from here to here, what is this? Now let's look at the h of e to the j omega. This one, we know it is a complex thing, right? So for complex thing, if you want to represent by real numbers, we have this one, h e to the j omega or equal to the real part of h plus j times the imaginary part of h j omega. Right. So basically we can write in this way. A complex number can be write as a real part and the imaginary part. Here's a j from in front of the imaginary part, right? And write in this way. Or equal to the magnitude of e to the j omega. We use 2 bar means to represent the magnitude. The same notation for absolute value. And then times e to the j, this is angle of h of e to the j omega. So we have this way. And in the graph way, you can think looks like this. This is h of e to the j omega. It is a complex number, right? So it has real part. This is real part. This is real part. This is real of h. This is real part. Alright. And this part is the imaginary part. Always be here. So this is the imaginary part of h of e to the j omega. So we have these two parts. And we can also use this way. This way is what? The length of this bar. This is the magnitude of h. I just write in this way. Alright. You know it is the magnitude of the whole thing. I just put h here. And this angle, this is angle of h. And the relation is what? This one, the real part is this length times cosine of this angle. You got it? This is just for the triangular, right? For triangular, how to define the cosine, the sine. This is definition of cosine, right? This is the bar, this h in the denominator, and this length in the numerator. The fraction is the cosine of this. In other words, this length times cosine of this angle equal to this. So the real part equal to this one times cosine of it. This one is a cosine. Cosine of this angle plus j times the sine of this angle. So we have this one. Right? We have this one. Alright? So we have this one. Okay, so this is the relation of that. And then when you have an input, if you want to find the output, you only thing is you need to calculate this one to find what is the magnitude, what is the angle. Alright, so we can use an example to explain it. Ready. I just consider this. Y of n minus y of n minus 1 equal to x of n. Now this is a system, right? This system. And we consider input x of n, which is e to the j omega 0 n, with omega 0 is pi over 4, for example. Here's 1/2. Pi over 4. Now what will be the output? Find the output. Okay, because the input is a sinusoid, right, with a unique frequency. So we know the output must be h of e to the j omega 0 times e to the j omega 0 n. Must be this. And what is this? This is a frequency response, right? Do you remember how to find the frequency response? You check the equation. You can write the frequency response directly from the system, right? From the equation. So here will be numerator related with input side is just 1, right? And output side is the denominator. It is 1 minus 1/2 e to the negative is a negative 1, right? Minus 1. So it is a negative j omega. Yeah, that's it. But now the omega I need is 0. So omega 0. And times e to the j omega 0 n. Now we have this. This is the first case. If we have a complex one, and of course we can plug in what is this one. 1 minus 1/2 omega 0 is 4 pi. So here's a cosine of negative pi over 4, not 4 pi, pi over 4, sorry. And plus j times sine of negative pi over 4. Right. Here's a e to the j omega 0 n. And we do some simplify. 1 minus 1/2 cosine negative 4 pi, negative pi over 4 is here, right? This is pi over 4. The cosine of it, that will be what number? This is this bar over this bar. So it is square 2 over 2, right? and j, sine of it, same angle. So this is a negative. This is negative one. So it's a negative square root 2 like that. So this is negative square root 2 over 2, things like this. And then e to the j omega 0 n. Right? We have this one. I can leave it here. I can also do some calculation to make this simple. This is 1 minus, okay, this square root 2 over 4. This is real part. And plus j times these two times together. It's square root 2 over 4. Here's 1. E to the j omega 0 n. Okay, so this is the output. Now you can just leave it here. And if you want to write this part, this is a fraction, right? This is fraction. If you want to remove the fraction, you need to do more calculation. But here you can just leave it here. It's fine. If you want, you need more. I write here, but I do not finish it. Plus j square root of 2 over 4 times the same number in the real part, and the imaginary part you change the sign. Here's a plus, you change to be minus. If here's a minus, here will be plus. Okay, you time this in the denominator, you also need to times this in the numerator. And this is the same thing. And you do some calculation. You can find the denominator part. After you times them out, you will find that the denominator is just the real number. Then this part over the denominator, is a real number. That is real part of the H, capital H. And this part, this one over the denominator, give you the imaginary part. Right? So you can have this. Okay, so this is the first input. Input is complex, output is complex. And the second one, input, I consider the case input, it is cosine omega 0 n, where omega 0 is pi over 4. Then what will be the output? Okay, in this case, you need, we know this one, right? Y of n will be magnitude of h times cosine of same frequency, but you add a phase here. Phase will be the angle of h. So we have this. But what is this and what is this angle? Alright, we need to do some calculation. Firstly, of course, you need to know what is the h of e to the j omega 0. You find these, then you find the magnitude and the angle. But here we already have the calculation, right? We have this. We already have this. It is this one. So we can find the magnitude from here and find the angle from here. Alright, now we'll see. Now h, h e to the j omega 0 equal to this one. It's 1 minus square root 2 over 4 plus j square root 2 over 4. Denominator is 1 over this. Right. So this is h of the whole h. Now what is the magnitude? So magnitude equal to magnitude of 1 over magnitude of 1 minus square root 2 over 4 plus j square root 2 over 4 magnitude. Right, it's a magnitude. Yeah, this is 1 and this bar means magnitude. For real number magnitude, it is just the absolute value. So this is just 1 in the numerator. And denominator, We know this, right? This is the magnitude. This is real part. This is the imaginary part. Right? Like this. So you see, what is this one? There will be square root of real plus square of imaginary to summation, then take square root. So it is a square root of 1 minus square root 2 over 4 square plus square of square 2 over 4. Yeah, this is the magnitude. This is magnitude. Okay, we can do a calculation. This is 1 minus 2 of it. That will be 2 times square root of 2 over 4. And the plus square of it, that is 4 over 16. 2 over 16, sorry. Square root takes square is 2, right? And the plus, this is a 2 over 16. So this is 1 over square root of, this is 1/8. This is also 1/8. So you do summation, you have 1/4, right? 1/4. So these two terms get 1/4. 1 plus 1/4. So it's 5 over 4. And minus square root of 2 over 2. Okay, that's it. You can leave it here. If you have calculator, you can find the value here, some value here. I just leave it here. And then the angle. What is the angle? We want to know the angle, right? Angle is here. Angle is here. So this one you can use. I know what is real, what is the imaginary part, right? So the tangent of it will equal to the real part over the imaginary part. So imaginary part is a square root 2 over 4, and the real part is 1 minus square root 2 over 4. Now you can have some value, and then the angle will be arctangent, right? Arctangent of this number. Now here I have to use a calculator or computer to do it. Let's go to MATLAB. MATLAB. Yeah, if you have calculator, you can also calculate it, right? So small size, I say. Okay, the first number is 1 over 5 over 4 minus square root of SQRT of 2 over 2 and square root of all of these. SQRT of this. Okay, this is a 1 point. Let me copy it. It is a 1 over square root of this, square root of this is 1.3572. And the tangent, that tangent, it is square root of 2. We can see both, right? Can you see both? Right. Yeah. Okay, so this one, this is a 1 over 5 over 4 minus square root 2 over 2. So yeah, this one. And this number will be square root 2 over 4 then over, do I need to put this together? This one is a numerator, and divided the denominator is 1 minus square root of 2 over 4. Okay, so I have point, this is a 0.5469, and then tangent of that angle equal to this. So this is arctangent of that. I can just put it in front of it. Arctangent of these so this is a arctangent of the, here's a 5469, get 0.5005. This will be in readers, right? The angle in readers. Okay, this were how many pi's? Pi is 3 or something, so like about 1/6 pi over 6, something like that, right? Something like that. Can I have it? If I divide by pi, 0.505 divide by pi, what it is? And okay, 0.1593. I go to reverse way. 6.27. Yeah, it's like 6. It's a pi over 6.2775, or it's a 0.1593 pi, things like that. So we have the angle. Then you plug in, you know the output y of n will be, the magnitude, this one is 1.3572, then times input is cosine, right? Times cosine, omega 0 is pi over 4, and here's a plus angle is 0.1593 pi. I think I need a negative. Do I need a negative angle? This one is plus or minus. This is a minus, so it's a minus. Here's this, or minus. Oh, it's a positive. This is positive, and this is a 1 minus 1 point. It's also positive. Angle is positive. Angle is positive. Okay, this is positive. I get something wrong. Oh no, this angle is I'm sorry, it should be minus. It's minus because this angle, is a real or imaginary, but I have 1 over it, right? 1 over it. So I calculate this part. I get the angle is the denominator's angle. So this is the angle. This is the angle of, not this one. This is the angle of the denominator. This is the angle of the denominator. I calculate by this one. This is not this one. The angle of the denominator. This is the angle of denominator. Angle of the denominator. Then this one will be it's 1 over that, so it will be negative of the denominator. So this is a negative. Angle is a negative 1. This is a positive, and this one equal to negative of it. This is the angle of this. So the angle of H will be negative of 0.1593 pi. So here's a minus. Yeah, that's what we good. So it is a cosine of pi over 4n minus these, things like that. Oh, here I use also I need a minus. I already have one over it. This is good. This one is good. This one I need a minus angle. Okay, so it should be this one. This is out of YN. We can also have a look. I have this edge, right? I have this edge. I use a computer to calculate directly. Actually here I only use a computer for the last step. I can also use computer from the beginning. From the beginning I have this one. And this is edge is this one. So I have edge for the omega 0 with omega 0 will be 1 over okay, I put this one here. Okay. I have edges here, right? This is edge. This is edge. This is edge. This is edge. So I just plug in here, I can have that edge. There will be 1 over 1 minus half times that exponential power inside is a negative j times omega 0. Omega 0 is pi over 4. Okay, oh, it's a minus, but yeah, this one. Okay, I get this one. And then absolute value ABS of HW0 actually is a magnitude, but the same name with the absolute value here. It's 1.3572. It's the same with our result, right? Yeah. So 1.3572, right? 1.3752. 1.3572, right, is here. And the angle of HW0 is negative. Yeah, negative 1. Should be negative. Negative 0.505. Negative 1. Then the output is just this one. If you want to find more, you can also use this way. G equal to we have a field, right? The system is this one. System is here. So the input side is just 1, and the output side, why you have two terms. The first one coefficient is 1, second coefficient is a negative half. Right, this is system. And you give the transfer function. Later we will learn what it is. And then we have input. I use a n run from 0 to, for example, I run 30 number. I use 30 number, and the input x is cosine. X is I use cosine, right? Second example, I use cosine. X is a cosine of omega 0, that is a pi over 4 times n. Right, this is the input. This is the input. You can see what it is. Plot of x, n and x, just x is fine. Plot x, yeah, this is x. Oh, this is I plot, so it's connected as a line. If I use stem of x, you will see the discrete time values, right? Discrete time values. I have this cosine. By this cosine as input, I have output y will be their linear similar. I use a system is g, input is x, and time duration is n. I have y. Or I have list out. Then I plot y. Yeah, same thing, right? It is also it's still a sinusoid, but it is not really cosine. It is shifted. You see the peak value is here. The original one peak value will be at the time equal to 0. The cosine start from 0 is the peak value, right? And 0 is peak value, but now shifted by an angle. That angle actually is 0.5. And the magnitude now it is not 1. Original signal is cosine, so magnitude 1. This one magnitude is here. Can I have the value? Look at that here. This is y, right? This is y. What is the maximum value of this y? See, maximum value. Maximum value of y is 1.3025. So the cosine is not, because the discrete time, right? So it will not reach the really peak of the cosine. Cosine peak will be here, something like here. Between these two, maybe the peak value is here. You see, peak value might be here, but discrete time you only have some balls, so you only have some value smaller than the peak. Peak should be 1.327, right? 1.357 or something. Okay, so this is what we did today. We discussed the output when input is a sinusoid. We start from the exponential, the complex sinusoid. Then we discuss sine and cosine in the real domain, right? Real signals. Okay. All right, that's all for today. I have two more minutes. Sorry for that. So okay. So bye bye. See you next time.